Hello, in this video I want to look at why the leading term of a polynomial determines the end behavior of that polynomial, and I am looking at the why. So let's say you're given a polynomial in just its general form. Powers are descending. So this is the leading term. 13x to the fifth is the leading term. And it will determine what direction the polynomial goes in, what they call the end behavior. Let me just show you what that means. So end behavior is when you're really, really far from zero. So your end behavior is like when x is, I don't know, in the billions or whatever, and either positive or negative. All right, that's what we mean by that. And so what is y doing? Is it going up, down, that kind of thing? So let's take a look. But before we get into it, I do want to just cover a couple of concepts. The rules of exponents. So what's happening is I'm going to actually input a number that's kind of big already, and I'm going to express it in scientific notation. So one of the things that will happen is, because you have polynomials that, you know, like x to the fifth, if I put something in that's like x squared, I'm going to have x squared to the fifth. So that's why I want to cover this rule of exponent. So recall that a power to a power, you multiply the exponents. So let's say I have 2 cubed raised to the 4th power, then I multiply 3 times 4 to get 12. Because essentially what's going on in the background is you're saying this input, 2 cubed, is multiplied by itself 4 times. So here's 2 cubed multiplied by itself 4 times. 2 cubed itself is 2 times 2 times 2, so you have that 4 times, and you have 2 12 times. So that's why you multiply the powers. The other thing I just want to make sure we remember is just scientific notation. And scientific notation is a way of dealing with really big numbers. And again, we're talking about end behavior, so we're talking about big numbers. Or very small numbers. So you might have a number like 0.000000072, you know, it's like a very small number. And it's either very large or very small because you have a lot of zeros before or after the decimal, right? So either to the left or to the right of the decimal. And I do want to mention that when we look at like the size of a number and we talk about the order of it, we're really looking at the power, 10 to what power. So let me just mention that if you were to win the lotto, you know, you could either win, let's say, $9 or $1 million. Well, obviously you'd want the $1 million, but 9 is a bigger number than a 1. But it's not really determining the size here, because what's determining the size are all the zeros, right? I mean, yes, I understand you'd love 9 million, but I'm just saying the 9 and the 1 aren't really what's important. It's really how many zeros are there. That's my point on that. So when you go to write a number in scientific notation, you express that number between 1 and 9 and then multiply it by a power of 10. So let's say I have this number here, 37,048. So I express it as a number between 1 and 10, which would be 3.7. And then I look at where the decimal point actually is, which is after the 8, even though it's not written there. And I say, how many times would I have to move over to get to 3.7? And I have to go 1, 2, 3, 4, which means I moved 4 decimal places, so that's a power of 4. So I want to write 3.7 times 10 to the positive 4 power, because that's going to be multiplying it by 10,000, so it's going to get it back. If I multiply this number, 3.7048 times 10,000, I'll get back to the original number, 37,048. I take a really small number, and it's really small because there's a lot of zeros to the right of the decimal. I first express this number as a number between 1 and 10, so that's 1.56. I look at where the decimal point is and how much would I have to move over, how many decimal places, and it'd be 6. So I multiply 1.56 times 10 to the, but negative 6, because I need to make it a small number, not a big number. So I want to divide by 10 to the 6. That's what 10 to the negative, multiplying by 10 to the negative 6 is. So that way, if I multiply this out, I'm going to get a very small number. All right, and just again to talk a little bit about the size of a number. So the power of 10 gives us the order or size of the number. So when we were looking at winning $9 or winning $1 million in the lotto, 9 is expressed in scientific notation as 9 or 9.0 times 10 to the 0. Anything to the 0 power is 1. So Here the order of the number is 0 versus a million is 1, 6. So you can see the order in difference is 0 versus 6. And that's because there's 6 zeros and there's no zeros here. Again, looking at the difference in the size of a number because of the power, difference in the power. 10 cubed is 1,000. And if you go from 10 cubed to 10 to the 4th, you're really saying I have 10 cubed or 1,000 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When I add that, when I add 1,000 10 times, there's my 10,000. So that's a huge difference, right? It's huge. Imagine then going from slightly bigger numbers like 10 to the 7th and 10 to the 8th. You already start with a big number, 10 to the 7th. And then you have that 10 times to represent 10 to the 8th. It's just huge, right? And that isn't even considered a big number. I'm talking about in behavior, I'm talking about really big numbers. That's just to give you that idea. So what I want to do now is look at a polynomial. I deliberately made the polynomial so that the first or leading term is negative and all the other terms are positive. I did that so that when we look at the largest number that we're going to look at as an input, it is the only number that contributes to the negativeness of the final answer, and everything else contributes to how positive the final answer is. And you're going to see all these numbers are outstripped by this one first leading term, and that's why the leading term determines the direction of the end behavior. So what I want to first do is start with numbers close to 0. So if you recall what I said, end behavior is really far from 0. So I'm going to start here, and I'm going to start with positive inputs. But I'm going to start here and then jump a little further out. And believe me, I'm not even close to this really far. So let's say I start at 0. So I have 0, 0, 0, 0, and then 20,000. So my final answer, y, is 20,000 when x is 0. What about when x is 1? Well, here I have negative 1 because I have 1 times 1 times 1 times 1 times this negative value. So, and then 500, 1,000, 600, 20,000. I get 22,099. Not a huge jump. Then I put in 10, and here's the contribution of each term. And so what I'm trying to show you is that for small values of x, the contribution of the leading term isn't that big compared to the other values, right? The other terms. So the contribution then of each of these is sizable compared to this. So this is your final value. But when you just get a little bit bigger, and I'm telling you, this is not a big number, but I used 1,000, which is 10 cubed, right? Times then this negative. Well, 10 cubed raised to the 4th power is 10 to the 12th, and then multiplied by this negative 1 on the outside makes this whole thing negative. So this is negative 1 times 10 to the 12th. And here I have 10 cubed, so that's 10 to the 9th, plus these other two zeros, that's 10 to the 11th. So it's 5 times 10 to the 11th, and then 1 times 10 to the 9th, and so on and so forth. When you add all these up, right, the contribution of each term to this final value, the final value in your calculator is going to be negative 4.99 e to the 11. What that means is, I'm going to round 4.99 to 5, so negative 5 times 10 to the 11th. Well, we went from positive numbers to all of a sudden a very negative number, and a big one, because it's got 11 zeros. So what happened is, this is still a relatively small input. For 1,000, for x equal to positive 1,000, what happened? The final answer, whether it was positive or negative, whether the final answer was positive or negative, ended up being determined by just this one leading term. And that's the whole point of this. And I don't have to compute everything here. I only have to look at how does this first leading term with the highest power, how does it behave? Meaning, what is y? Is y going to be positive or is y going to be negative when I put in a positive x or a negative x? That x is big. What's it going to do? What's the polynomial going to do? So that's really what we're looking at. In the end behavior, for x positive, does y go positive or does it go negative? For x negative, does y go positive? Does y go negative? And we determine that behavior by a. I'm sorry, not by a, by the leading term, a x to the n. So here is just a little chart to kind of put it together. First of all, this squiggly part they have in the middle of each of these graphs means that it's the inputs of x that are not that big, right? Because we're looking at very big x positive, very big x negative. But if x is even power, well, what that means is no matter what I put in for x, whether x is positive or negative, because I raise it to an even power, I get a positive number. So what's going to determine the direction is the coefficient a. If a is positive, then y is going to be positive. If a is negative, y is going to be negative. Let me just give you an example of that. Suppose we have here, x to the fourth, and I have a negative on the outside, which is understood to be a -1. If x is positive, positive times positive times positive times positive, this part is positive, but then I multiply by this negative number, then the whole thing is going to be negative. And if x is negative, because I multiply it by itself a negative number of times, I still get a positive, and then I multiply by a negative, so I get a negative. So what really determines when you have an even power, because no matter what input you put in there, what's going to come out is positive, meaning the x to the fourth is positive. What determines the behavior is the coefficient of a sub n. So when you have an even power, if a is positive, that means y is going to be positive on both sides in the n behavior. If a is negative, y is going to be negative in the n behavior. Now, if you have odd, meaning an odd power, like x cubed or something, then what you have is, if a is positive, then what determines it is the actual x to the third power. If x is positive, when you cube it, for example, it's going to be positive. If x is negative, when you cube it, it's going to be negative, and the a isn't going to change anything. It's going to just keep the sign. Versus here, if you have, for example, x cubed, and you have an odd power, if x is positive, you have positive number multiplied by itself 3 times, it's positive, but then you multiply by negative, then the whole thing goes negative. Excuse me, if x is negative, multiply, let's say, -2 by itself 3 times, it's going to be -8, but then you multiply by a negative coefficient, it's going to make it positive, so it's going to flip this, right? It's going to be like that. So I have negative x cubed, is negative, and you have an odd power. If x is positive, it's like +2, you have 2, 2, 2, that's +8 times a -1 from this negative on the outside, you have a negative. So if x is positive, like +2, positive, but then you multiply by negative, it goes negative, it's -1. If x is -2, then you have negative times negative times negative is positive, but then times this negative on the outside, it's going to make the whole thing, I'm sorry, if negative times negative times negative is negative, and then when you multiply it by negative, it's going to make it positive. So -2 ends up being positive. So this is just a little part to kind of put it together. And this is not about the middle behavior, it's about the end behavior, right? So let's take a look at some examples. Here you have x to the 6th is the highest power. Let me get that little chart out. So what this means, this is my leading term. The x to the 6th is always what? Positive, no matter what. Whether x is negative or whether x is positive. When I multiply that number by itself 6 times, it's going to end up being positive. And then I multiply it by a positive 2/3. That means this whole thing is positive, regardless of whether x is positive or negative. So what that means is I don't care about this behavior. X is positive, this thing is positive, the y is positive. So x is negative, y is still positive. So you get this behavior. That's this one. Here, if you have an even power as the highest power and you have this leading term, but what happens here is this part, x squared, is always positive, but then you multiply by this negative, so this whole thing is always going to be what? Negative. So what that means is, outside of the middle behavior, if x is positive, y is still negative. If x is negative, y is still negative. So you have this behavior. And you look at the odd powers with either a negative or positive coefficient. And here, if x is positive, then x to the 7th is positive, right? Because you have a positive number multiplied by itself 7 times, that's positive. But then you multiply by negative, then y is going to be what? Negative. What that's saying is I have an odd power, and here I have a is negative. So when x is positive, my y ends up being negative. If x is negative, then x to the 7th is going to be negative, because you have a negative number multiplied by itself 7 times, it's going to be negative. Then multiply it negative outside here, negative 5, y is going to be what? A negative times a negative, it's going to end up being positive. So again, it's under the case that the power is odd, 7, and a is negative. So if x is negative, y is positive. Here, even power, but positive a. So if x is positive, cubed is also positive, and then times positive 8, y is positive, right? So this is saying if x is positive, I'm here, y is positive, so I'm going like that. And here, if cubed is negative, right? A negative times a negative times a negative is a negative. And then you multiply it positive 8, y is still negative because it didn't change the sign. So here, if y is negative, so I'm negative, and then y is what? Negative, so it's like this. Odd power, positive, you get this shape. So the main point of this then is you really look at the leading term, and then you have to think about the power and whether the a is positive or negative, and combine those two to see what's going on. And then you'll know the end behavior for very large x, or very large x positive, or very large x negative. Thanks so much for listening.